Z-scores. Example 1. At one point, the Scholastic Aptitude Test, SAT test, which is a test that colleges use to decide which students to admit. At one point in time, the mean was 900 with a standard deviation of 200. At that time, the American College Test, ACT, had a mean of 25 and a standard deviation of 5. If Fran scored 1300 on the SAT, how many standard deviations is Fran's score above the mean? In other words, what is Fran's Z-score? So there's a formula we can use. It's a score minus the mean divided by the standard deviation. So Fran's score was 1300, and the mean was 900 for the SAT test, and the standard deviation is 200. So 1300 minus 900 is 400. So it's 400 divided by 200, which would be 2 standard deviations above the mean. So Fran's score of 1300 was 2 standard deviations above the mean, and that's actually a pretty good score. Part B, Sandy scored 40 on the ACT test. How many standard deviations is Sandy's score above the mean? In other words, what is Sandy's Z-score? So we can use the same formula. The Z-score is the score minus the mean divided by the standard deviation. Sandy's score is 40. The mean for the ACT test was 25, and the standard deviation was 5. So 40 minus 25 is 15. 15 divided by 5 would be 3. So Sandy's score is 3 standard deviations above the mean. So which student did better compared to others taking the same test? Well, Sandy would have done better. Sandy's Z-score is 3. 3 is more than 2. Sandy is 3 standard deviations above the mean. So the answer would be Sandy, because Sandy's Z-score was higher. Sandy's raw score was lower. 40 is lower than 1300, but that's because the tests were scaled differently, and 40 on the ACT means something different than 40 on the SAT. So the Z-score gives us a way of comparing numbers from different data sets with different means, different standard deviations. Okay, so there's a couple of theorems related to Z-scores. One is Chebyshev's theorem. We're going to focus on Z-scores of 2. So Chebyshev's theorem can apply to any Z-score, but we're going to focus on Z-scores of 2. So this is Chebyshev's theorem part 2. For any distribution of numerical data, at least 75% of the data is within 2 standard deviations of the mean. In other words, at least 75% of the Z-scores are between -2 and 2. And the picture can sort of help your understanding here. This curve here is what's called a probability density function, and the probability corresponds to the area underneath the graph. So between -2 and 2, we have at least 75% of the data, and then at most 25% would be at either extreme. Okay, so in this example, we assume SAT scores have mean 900, standard deviation 200. Use Chebyshev's theorem part 2 to estimate the proportion of Z-scores that are less than 1300. Okay, so the Z-score for 1300 is going to be 1300 minus the mean, which is 900, divided by 200. And that's going to be 400 over 200, which is 2. So the proportion of Z-scores left to 2, if we look at the picture here, at least 75% are less than 2. So from the picture, at least 75% of the Z-scores are less than 2. And so that means that at least 75% of the SAT scores are less than 1300. So Sandy actually did better than at least 75%. I mean, Fran did better than at least 75% of the students. Now, if the graph is bell-shaped, we have a stronger theorem. This Chebyshev theorem applies to any data set. But if the graph has a bell shape, then we can have a stronger result. This is empirical rule part 2. It applies to bell-shaped graphs, and that says, and we're going to focus on part 2, empirical rule part 2, that applies to z-scores of 2 or -2. Again, the z-score could be other numbers. That doesn't have to be 2 or -2, but we're going to mostly focus on 2 and -2 because that's kind of the borderline between unusual and not unusual scores. So, okay, so for bell-shaped graphs, 95% of the data is within 2 standard deviations of the mean. So it's 47.5% on each side. And then at the 2 tails, we have that leaves 2.5%. So we have 2.5% of the z-scores are less than -2. 47.5% are between -2 and 0. 47.5% are between 0 and 2. And 2.5% of the z-scores are more than 2. So this applies to bell-shaped data. Okay, so again, we're going to assume these SAT scores have means 900 and standard deviation 200, but we're also going to assume that they're normally distributed. In other words, they have a bell-shaped graph. And we want to estimate the portion of SAT scores that are less than 1300. So the z-score for 1300 is 1300 minus the mean, which is 900, divided by the standard deviation, is 200, 400 over 200, which is 2. So if you look at the picture, the percentage of z-scores less than 2, well, we have the 2.5% plus the 47.5% plus the 47.5%. So that's 2.5 plus 47.5 plus 47.5, and that's going to add up to 97.5%. So if the SAT scores have a bell-shaped graph, 97.5% of the z-scores are less than 1300. So if it's a bell-shaped graph, then that's Fran's score of 1300 is looking even better. It's better than 97.5% of the data. Okay. Okay. So the Triola's range rule of thumb part 2 sort of combines Chebyshev with the empirical rule. So it's kind of a way of summarizing it. And with Triola's range rule of thumb, he's not as precise. We don't know if it's bell-shaped or not bell-shaped, so we don't really know how extreme these z-scores of -2 and 2 are. But whether it's more than a z-score of 2, whether it's more than 75% or more than 97.5%, either way, anything above 2, we're going to say that's unusually high, and anything below 2, -2 would be unusually low. Z-scores between -2 and 2, we're going to say are not unusual. So it's Triola's range rule of thumb is sort of a loose way of describing and combining the empirical rule with Chebyshev's theorem. So we're going to say z-scores less than -2, unusually low, between -2 and 2, not unusual, z-scores more than 2, unusually high. Again, we're going to assume SAT scores have a mean of 900 and standard deviation 200. Fran scored 1150, Fyrus rather scored 1150 on the SAT. Triola's range rule of thumb to determine whether Fira's score was unusually low, unusually high, or not unusual. So the z-score for Virus is 1150 minus the mean, which is 900, divided by the standard deviation, which is 200. 1150 minus 900 is 250, divided by 200 is 1.25. So that 1.25 is between -2 and 2. -2 and 2, so it's not unusual. According to Triola's range rule of thumb. Okay. Okay, so according to Triola's range rule of thumb, a score of 2.1 would be unusually high. So we have 2.1 is more than 2, so that's unusually high according to Triola's range rule of thumb. What SAT score corresponds to a z-score of 2.1? So in the previous example, we were given the x-score, and we used the formula to compute the z-score. Here we're kind of reversing that process, where we're not given the x-score, but we're given the z-score. So we want the score minus, we can use the same formula. The z-score is the score minus the mean divided by the standard deviation. But now we want to solve this for x. So we want to multiply both sides by 200. I'll do it over here. X minus 900 over 200 times 200 equal 2.1 times 200. Well, I'll do it down here. I'm running out of room there. Okay. Okay. So on the left side of the equal sign, the 200s will cancel, and we're just going to have x minus 900 equals, and 2.1 times 200 would be 420. And then we want to add 900 to both sides to isolate the x. And that will give us x equals 1320. So the minus 900 plus 900 will cancel. And so an SAT score of 1320 would correspond to a z-score of 2.1 and would be unusually high. So this is a score of 1320 would be unusually high. And let's do an unusually low z-score. So again, according to Triola's range rule of thumb, a z-score of negative 2.3 would be unusually low. So negative 2.3 is less than negative 2. That's unusually low. So we want to find out what x-score corresponds to that z-score. So again, we want to solve the z-score is the score minus the mean divided by standard deviation, x minus 900 over 200, and we want to solve for x. So we want to multiply both sides by 200. And again, the 200s will cancel here. And that'll leave us with x minus 900 equals negative 460. And then we still want to isolate the x. We want to add 900 to both sides of the equal sign. And minus 900 plus 900 is 0. That will drop out. We just have x by itself on the left side. And Here on the right side, the signs are different, so we subtract. Negative 460 plus 900 is going to be positive 440. So an SAT score of 440 corresponds to a Z-score of negative 2.3, and that would be unusually low. And that concludes this presentation.